So, yeah, so chapter 14 is actually, the title of the chapter is multiple integration. So really we'll do double integrals and then triple integrals later, but we'll start with double integrals, multiple integration. And we'll talk about what it means, but I always have sort of two things on my mind. How do you do it, and then what does it mean? So I'm going to make up a problem. This is a double integral I'm going to make up. I'm going to put a function in here to integrate. It's a function of several variables. We're still kind of working with functions of several variables, but now we get to integrate. I'm just going to make one up here, which doesn't always go good sometimes. Wow, yeah, this might not go too good. Let's see. And then so here's the function I'm integrating, and I'm integrating it with this order of integration, dy dx. I'm integrating this function. I'm going to put some bounds on here, and what you have is sort of an inner integral and an outer integral. And when we start working on it, what you'll see is we'll do the inner integral first, and then we'll get the answer, and then we'll do the outer integral. Now the bounds for this inner integral, I'm going to put, I'm going to make it 0 to x, and then 0 to 2. And I'll explain kind of what all that means, but let's just do the integral first. So I made up this integral, and now I want to do it. And let's see. So what it says here is I'm going to work on integrating this. You know how we did partial derivatives? Yeah. When we did a partial derivative, we would hold somebody constant. Well, that's kind of what this is. This is partial integration. So you work on this inner integral first, and what it says is you're going to do this inner integral with respect to y. Mm-hmm. And so that means we're going to treat y like the variable and integrate with respect to y, and we'll treat x's like they're constants. Mm-hmm. So here we go. Okay, now by the way, we are integrating all of a sudden. I mean, this is a big shift in gears from what we were doing last week. We were differentiating, now we're integrating. With respect to y, when you integrate, you go y squared over 2. Mm-hmm. Yeah, so y squared divided by 2 will make that a 2x squared y squared. Yeah. Hey, I'm integrating this with respect to y's. It's just a big old constant. So how do you integrate a constant with respect to y?
Minus 3y cosine 2x.
You just multiply by y. Mm-hmm. I mean, when you integrate a 6 with respect to y, it's 6y. So when you integrate this constant with respect to y, you get 3y. You want to multiply by y. Right. That's a good place to multiply it right there. Sure. All right, now I'm integrating, I'm integrating this with respect to y. So I'm treating the x like a constant.
1 over y.
Oh, small x.
1 over x, you get the xy. He's right.
Yeah, this is confusing. Hang on. When you integrate an e to the 2x, how do you do it? You get e to the 2x, but the u substitution spit out a 1/2. Do you remember that? You do a little u substitution on the 2x, and then the du is a 2 dx, and then I like to solve for that, so 1/2 du equals dx. This is worth doing here a second. Okay, I know this is pretty basic, but it's been a while. Hang on, this is me integrating this. When I plug it back in, hang on, when I plug it back in, I get e to the u, right? I call that u. And then what's the dx?
Okay, 1/2
oh, 1/2 du. So I'll pull the 1/2 out front, and then I got du. Now when you integrate e to the u, the answer is e to the u with a 1/2 out front, which is what we said. Okay, cool. All right, so now, hang on. You're saying that's what he is. He's just himself, e to the xy, but the variable was y. The x was treated like a constant, so you think it spit out a 1 over x. Yeah, I agree. It spit out a 1 over x. All right, that's awesome. That's the inner integral, and now the inner integral has these bounds from 0 to x. So I should evaluate this from 0 to x, and who am I sticking these bounds in for?
Y.
For y, right. Y is the variable. So I'm plugging these bounds in for y. Here we go. When I plug in that x, I'll have x to the fourth, 2x to the fourth. When I plug in that x there, I'll have a negative 3x cos 2x. Okay. And when I plug in that x there, okay, 1 over x e to the x squared, I guess. Right, you guys? Yeah. Minus, I should plug in a 0 for y. A 0 for y. If I plug in a 0 for y, that's a 0. That's a 0. But when I plug in a 0 for y here, e to the 0 is a 1.
And then the 1 over
And so, 1 over x. Wow. Okay, the problem's over. Whoa. The inner integral is over. And what you have sitting here now, notice all the y's are gone. All the y's are gone, and that's, you integrated with respect to y. Y was the variable. All those y's got replaced with x's, and that's kind of typical. When you evaluated it with these bounds, bless you, when you evaluated it, you plugged in, all the y's got replaced with x's. So now you don't have two variables anymore. You got a single integral from 0 to 2 with respect to x, and it's just a bunch of x's. So now I got a problem though. I got a problem. Houston, there's a problem. Yeah, I got a problem. I don't know how to integrate some of this stuff. Actually, just one of this stuff. Yeah, I don't know how to integrate this guy. I'm sorry. I quickly threw this problem up here. I didn't think it out too well. I can't integrate that.
Everything else you can. What I call that an earth?
Yeah, I don't know what. Yeah, with that 1 over, I can't integrate that. So I made up a bad problem.
Would we, if we came across something like that, would we integrate everything else and call that like the earth that we learned in D? Or
Well, it's not quite that, and we should be able to integrate what we can integrate. So this shouldn't happen. It's just that I made up a quick problem and didn't think it all through. There's some other good stuff happening here. I wonder what I should do here. I want to
just make it y.
Yeah, can we just change the problem?
Yeah.
All right, hold on. Let's change the problem. So if I go back to this original problem, can I make it an e to the y? Okay, so how do we integrate an e to the y with respect to y? How do we integrate an e to the y? It's just e to the y. Yeah, it's easy. That would have been a lot nicer. So now it's just e to the y? Now wait a minute. And then when you plug in an x and a 0, I'm plugging in an x and so I'm changing the whole thing. I'm sorry, you guys. But it's easy on a whiteboard. It's tougher for you. When you plug in an x, now it's e to the x, right, you guys?
Minus 1.
Minus, and way down here at the end, when you plug in a 0 for y, I'm plugging in a 0 for y. That's a 0, that's a 0, but e to the 0 is a 1. So now I'm changing this answer here. It is a plus e to the x minus 1 is what I'm doing. Integrating this with respect to x. You guys all right? Sorry about that. Okay, so now we're just integrating with respect to x. Anybody know how to integrate 2x to the 4th?
2/5 x to the 5th.
2/5 x to the 5th. All right, awesome. Anybody know how to integrate 3x cosine 2x?
Tabular method.
Ooh, good. I would do integration by parts. But a shortcut for integration by parts is the good old tabular method. So you're right. So that's a problem all in itself. I'll tell you what, let's just skip that a second. let's just skip that. Let's move over. Can you guys integrate the e to the x? E to the x?
Yeah.
And can you integrate a 1?
Minus x.
A minus an x. And then we're going to evaluate this from 0 to 2. So everything's cool? Okay, but let's work on this. We do have to integrate this, and technically it's a little integration by parts. But I like to do what's called the tabular method, where I make a table, and I put u here. And I think I'm going to call that u a negative 3x. I guess I'm going to keep the negative sign with that. So it's a negative 3x, and then I take derivatives until I get to 0. The derivative is negative 3. The next derivative is 0. Well, then that means I'm calling dv, I'm going to call the cosine of 2x. And now I have to do little baby integrals here. I got to integrate to get v. I have to do a little integral of cos 2x, an integral of cos 2x. I think that's sine 2x, but it spits out a half.
That's not negative.
Yeah, 1/2 sine 2x. All right, now I have to integrate sine 2x. I think that's negative cos 2x, but it spits out a half. Negative 1/4 cos 2x. Are you guys okay? And then over here you put plus, minus, plus. This is just, it's called the tabular method. It's a shortcut for integration by parts. It can be used only in special situations. But now the answer is this. You grab this term, and then you drop down here, and this is one multiplied term, one term here. And then here's the next term. And we're done. So what is that? That's a negative 3/2 x sine 2x. A negative 3/2 x sine 2x. And what else is it? A positive, oh no it's not, a negative, see that negative? Negative 3/4 cos 2x. Negative 3/4 cos 2x. That's the answer to that took a little effort. How you guys doing? Any questions? All right, hey, let's evaluate it from 0 to 2. I don't have, I mean, this is going to be a little weird also. I'm plugging into 2, and it's 2 radians. There's no degrees up there. Anyway, let's work on this. If I plug in a 2, it's 32 times 2. That's 64/5. If I plug in a 2, let's see. 2 is going to cancel. It's going to be a negative 3 sine of the number 4. That's what that is when you plug in a 2. And then that's 4 radians. I don't know, whatever. It's some nasty decimal. Minus 3/4 the cosine of 4. Plus e squared. Minus 2. Wow. Minus, what happens when we plug in a 0, you guys? You gotta watch out. Sometimes you got a habit of thinking everything's 0, but let's see, that's a 0. That's a 0. Hey, the cosine of 0 is a 1. So that's a negative 3/4.
And then plus 1.
And that's a e to the 0, that's a plus 1. And then that's a 0. We're finished. Whatever the hell this number is. It's 64/5. I mean, I can't do much simplifying here. Minus 3 sine of 4 minus 3/4 cosine of 4 plus e squared. Oh my goodness. This used to be my number on the high school swim team. Minus 2. Hang on, I'm going to add this up. Minus 2 plus 3/4 minus 1. That's a negative 3 plus 3/4. That's a plus 9. No, negative 9/4 is what that is, I think. I guess I could get a common denominator. I mean, I do have 2 numbers here I could add up. I can't really, this is my exact answer. It wouldn't hurt to tell me roughly. It's just a number, you guys. It is a number. 12.7 or, I don't know what it is. Anybody know what it is? It's got to be in radians. Okay, let's try.
20.7.
20.7. Yep. All right. That's roughly what that is. Cool. Now, what does that mean is probably your next question. I mean, we just did this double integral. I changed the original problem back to the, okay, yeah. We did this double integral. You know, what is this thing here that I'm integrating? This thing I'm integrating is a function of x's and y's. What's another name for that? Z, right. So this is some function of a couple of variables here. This is z, which, you know, that's a surface. This is some surface in 3D. And then I'm integrating with respect to y and x. So I'm kind of integrating over the xy plane, and the bounds for y and x are described here. Now here's what these bounds say. I want to show you what these bounds say. They say that y, you know, the bounds for y were 0 and x. So my y lives between 0 and x. I mean, that's what that says. And then my x lives between, because my bounds for x are 0 to 2. So then my x lives between 0 and 2. You know, this is an interesting, this describes a region in the xy plane is what this describes. This describes a region in the xy plane. I'd like to draw that region. That's not a very difficult region. Sometimes they get kind of difficult. Let me think here. In the xy plane, what did we say? So y is between 0 and x. Do you know how to draw y equals x?
Mm-hmm. Just a straight up slope of y.
Yeah, here's y equals x. And so they're telling me y lives between y. Hang on. Y lives between 0 and x. So that's y. Y lives between, here's y equals 0 right here, right you guys? Mm-hmm. So y lives between 0 and x. Here it is. It's all this stuff in here, between 0 and x. Oh, except wait a minute. It's not infinite. X lives between, x lives between 0 and 2. So hang on, that's x. Now, you know how x moves. X moves sideways, left to right. So x goes from 0 to 2. I'll just I'll sort of mark that at 2. So it's here. It's not this. It's this region. Well, x is between 0 and 2, and y is between 0 and x. It's this triangular region. What's this triangular region? That's what I'm integrating. Listen, I'm integrating this surface over this region. See, this is z equals, right, you guys? Mm-hmm. So there's some surface living up here above this, and I'm integrating that surface, but I'm only integrating the portion of that surface that lives over this region. And that number is the volume of that thing. Now see, I'm not drawing that whole 3D thing, but there's a surface that lives above this region in the XY plane. And that's the volume of that. Cool, huh? I mean, let me see, can I draw a 3D picture of it? Hang on, in 3D world, what am I doing? I'm on the x-axis over here. 1, 2. I go up here and oh, here's my triangle. This is my triangle, right, you guys? It's a little triangle button up. This is y equals x in the xy plane. And there's a surface up here. This is the part I'm going to be fuzzy about, but there's some surface living up above this. It's some infinite surface probably, but I'm only looking at this volume You know, it's cool. It's got this triangular base, and it's really got these triangular sides until it hits the surface, and then it's got this weird ceiling. You could call the surface the ceiling of this thing. But everything's nice and straight up until it hits that surface. The surface is the undulating, curvy surface, which I didn't draw specifically. I just sort of generically drew a surface up there. Hey, that's pretty cool. We just found the volume of this shape. It's got this triangular base. It's got these triangular kind of sides, but it's kind of got this funny little roof. And we got the volume of that. 20.7. That's good now, and that's the truth. I told you the truth. I didn't lie to you. You know what the book does? They lie to you. Nah, I'm just exaggerating. But they open with these double integrals, and they really, in 14.1, they don't act like you're finding volume. They don't act like this. They act like you're finding area. And you kind of can find area. But here's the funny thing. Do you know how to find area already? Do you need double integrals to do area? Haven't you done area in Cal 1? And you don't need double integrals to do area. All right, but they open in 14.1 and they show you how these double integrals can help you find the area of a region. I kind of got to the point, and I guess I jumped to 14.2 when I actually did a problem. When you actually are integrating a function over some region described by these bounds, it's really the volume, it's really that volume that I described. See? Okay. So I kind of, here's generically, you sort of talk about these double integrals like this. It's a double integral over a region R. You're saying you're going to do this double integral over a region R, and you've got some function, f of x, y, again, that's z. You're going to integrate this function, and you're going to integrate it with respect to a, dA. And that's kind of, you're going to integrate this function with respect to a, the area of that region R. You're going to integrate this function over the region R with respect to the area of that region R. But when you do that, I hope you see a surface up above a region R, and this is technically the volume. Let's just say it. This is technically the volume. Okay, this is the proper way to say this. The volume of the solid bounded by the surface z equals f of xy. That's one of the boundaries. And what else? What's the other boundary? The region R in the xy plane. The region R in the xy plane. That's what this is. This double integral is the volume of the solid bounded above, or usually bounded by the surface, and the region R in the xy plane. I just got done sort of saying all that and drawing all that, but there it is, a little more official. But that's really 14.2. Listen, in 14.1, they do this. Watch this. They don't put a function there. In 14.1, you kind of don't have a function. Well, they throw some in there, but because they're trying to get you to learn how to integrate. They're trying to get you to, but when it comes to a lot of problems, they just put a 1 here. There's nothing there. There's no function there. And it's dA, and it's over the region R. And then we say that this double integral is the area of the region R. That's what we say. But we're sort of lying. Listen, I wonder if you can get this. So So watch this. So in this picture, right, you got some, you're integrating over some region R, you got some function up above here, and you're finding this volume. Are you guys okay?
Mm-hmm.
I mean, I just had this picture kind of here. Now I got this generic picture. And that really is volume. Okay, watch this one. So this one, I'm integrating. I got this region R in the XY plane. Watch this. I got this region R in the XY plane. And then, you know, on that top one, I had Z equals f of xy. That was my height up there. That Z equals, my function is my height. What is my Z in this one, if I wanted to think of it?
1.
Z is 1.
And isn't that just it?
So I'm integrating something that has a height of 1, and it's not changing. It's not a bunch of variables. It's not some undulating surface. I'm integrating Z equals 1. And Z equals 1 is just, you know, a flat plane, you know, at Z equals 1. And so I'm integrating this shape. Oh my God. There's the region R, and then I'm integrating this thing at a height of 1. This is just Z equals 1. If that area of that base is, let's just say that area is 14, what's the volume of this thing?
14 times 1.
If it has a height of 1, right, if the area of the base is 14, if the area is 14 and it has a height of 1, what's the volume of this thing?
14 times 1.
14?
Mm-hmm.
Are you with me?
Mm-hmm.
When something has a height of 1, its volume is its area, right? All right, that's their little lie. That's their little trick. When they say that this is the area of the region R, that's cool. We'll go with that. We'll talk like that. But the truth is, I would say it's the volume of something with a height of 1. But the volume of something with a height of 1 is numerically equivalent to the area of the base.
Mm-hmm.
Does that make sense?
Yes.
Whew. Good. Every semester I'm worried if I can explain that or not.
Mm-hmm.
It's a double integral. I'd like to, double integrals are volume. But they mess with me a little bit in 14.1. They tell me it's area, and I see their game now. It really is volume of something with a height of 1, but we can interpret that as the area of the region. Numerically, it's the same. If I wanted you to find, so let's do some area, okay? Let's do some area. I'm going to put this in my notes here. This is 14.1, kind of, and then this is sort of 14.2. But I like to do it all at once in a way, like I just sort of did. I hope I didn't confuse you. So, watch this. So I want to do the area of this thing. I'm just making up sort of a problem here. I'm going to call that A and B. And I'm going to call this f of x and g of x. And I want this area. Now, just go back to Cal 1 or Cal 2. And how would I find that area?
Rectangles. Or integrate.
Just do an integral, just a single integral.
From A to B.
From A to B.
And then that would be
If you remember, you learned
G,
to do area between two curves, you would learn how to do.
F of x minus G.
Yeah, top minus bottom was what I would say. We would do the top function minus the bottom function, and we would get the area. That's how you get the area between the two curves, right? Okay, so that's Cal 1. That's how you do it in Cal 1. Or like I said, the beginning of Cal 2. That's how you do area. Yeah, okay. Okay, let's do it with a double integral. which means I guess I'm sort of doing this. Hang on. I'm doing this. I'm doing a double integral, and I'm going to put a 1 in there. All right, hang on a second. So I can do a double integral. I'm going to put a 1 in there. Now, this dA, you guys, this dA that shows up in this sort of generic formula here, the dA is, well, it's either a dx dy. You only saw me do one example today. It's either dx dy or it's dy dx. That's what the dA is. I think the one example that you saw today was I did dy dx. And if you let dy dx, if you do it dy dx, that means you're letting y go first and you're letting x go second. And dx dy, we'll do several, we'll switch them and we'll do dx dy also. That means I think about my region differently. I have to think about my region with x going first and y going second. And see, the guy who goes first has to be more generic than the one who goes last. So let's just try to do this. I think I want to do this one, dy dx. So what would be your bounds for y? If I thought about y, like a y stick here moving. I mean, I need my lower y and my upper y. Those are my bounds for y. I mean, you haven't had practice setting up bounds yet. I did a problem that already had the bounds set up, but this is a skill you need. When you look at this picture, the lower y would be g of x, and the upper y would be f of x. And it's like we're gonna get that rectangle there with a lower y and an upper y, and then we're gonna let that rectangle go all the way through this whole region for my left and right bounds for x. What would be your left and right bounds for x? From A to B. Again, you only saw one example so far today, but in that one example you saw today, I don't know if you remember, but the y bounds had x's in them, and then the last bounds were just numbers. My one problem I did was 0 to x, and then it was 0 to 2. And that's how it usually works. These inner bounds are in terms of these bounds for y are in terms of x. And then the bounds for x are numbers. Now, do this problem. Let's do it. How do you integrate with respect to y? You're integrating a 1 with respect to y.
Y.
You get a y, okay? You get a y. And then you're going to evaluate it from g of x to f of x. So what are you going to do? Plug in your f of x, plug in your g of x, and subtract them. So then what are you going to have? You're going to have f of x minus g of x. And then you still got an integral to do from a to b with respect to x. Right, you guys? Well, look what just happened. After one step of the double integral, boom, you're back to Cal 1. You with me? Okay. All right. Here, let's do a couple more problems. I'm in 14.1 then. I'm in 14.1. I think I explained all that pretty well, but we need to do a problem. Ooh. See, what happens is you end up having to integrate, you guys. This is kind of tough. You know, I'm going to grab this 26. This is kind of a tough way to start, but 26 in the book looks like this. It's a double integral, and it is 0 to y, 1 to 3. Listen, 0 to y, 1 to 3, and then the integrand is 4 over x squared plus y squared dx dy. 4 over x squared plus y squared dx dy. Wow, that's pretty tough, you guys. It might be tough. First of all, let me just ask you this. So at the beginning of this section 14.1, they do have a bunch of double integrals they want me to do. And so they do have functions in here, but they're not asking me to interpret what it means. I've already spilled the beans of what it means, though, haven't I? So can you tell me what this one, if and when it ever gets finished, it'll be a number, and what will that number mean?
The volume.
Thank you. Because it has a function in there, you're integrating a function over a certain region. Thank you. This really is volume. But they're not asking about that at first. They're just trying to get you to do the mechanics of doing the integral. Hey, and if this function wasn't there and it was a 1, then you might say it's area, I guess. Area of whatever region is described right here. But, okay, all right. Hey, so here we are. We're trying to integrate with respect to x right here. I think it's arctan. Great. Out of the blue, out of the magician's hat. I think you're right. I think this is an arctangent. I have to pretend y is a constant. The 4 comes out. It's an arctangent of x over y. That's how you do it. Now, does arctangent have a, see, it's x over a, and my a is usually a constant, and my y, I'm treating my y like a constant. This is the arctangent of x over a. Does it have a 1 over a out front?
Sure, I think it does.
Yeah, it does. It has a 1 over a out front. So what's that? A 1 over y out front?
Yeah.
Wow, that's a trip, you guys. That's an arctangent.
So we're saying that, well, yeah, okay. So we're saying the y squared
I'm
is
treating the-
technically a squared.
I'm treating the y like it's a number, like it's a
Such
constant.
as a.
I'm integrating with respect to x, so I'm pretending it's a 2 squared or a 3 squared or an a squared, and I remember the rule for arctangent. It was x over a, 1 over a out front. Yep. Wow. All right. You might not have to remember arcsecant, but arctangent might pop up like it just did. Hey, now what do I do?
You're going to evaluate from 0 to y.
I'm going to evaluate from 0 to y, which means I'm plugging in the 0 and y, and I'm plugging it in for who? See, it gets confusing. Who am I plugging it in for?
For your axis.
Oh, my x's, yeah. I'm plugging it in for x. You're right. Okay, I'm plugging it in for x. So when I plug it in for x, I get this 4 over y, arctangent of y over y, which is 1, minus 4 over y, arctangent of 0. Is that what I'm doing? Plugging in as, yeah, arctangent of 0. All right, well, I should be able to handle this, you guys. I should. The arctangent of 1 is very famous. The arctangent of 1 is very famous. It's a famous angle. What angle is it? It's a very famous angle.
45 degrees.
Yeah, 45 degrees. Arctangent of 1 is 45 degrees. I'm going to call it pi over 4. You know what the arctangent of 0 is? Your calculator helps you, though. You're right.
That'll be
It's a 0, I think.
0 degrees.
Hey, these 4's cancel. I just did the inner integral, and look what my answer is. Pi over y. And I ain't trying to rhyme. It's just that time. Pi over y. Wow. Now what?
Integrate again.
Oh, integrate again. And now I'm integrating with respect to y from the bounds 1 to 3. That's pretty much a trip, you guys.
1 up to pi. And then you have out in the y.
Yeah, how do you integrate a pi over y? I think it's the pi ln of y. From 1 to 3. This does kind of sound like Dr. Seuss. And then you get the log of 3 minus the log of 1 is a 0. We're done. Pi log 3 is the answer. That's a number. It's a number. Pi log 3. I guess it's technically the volume of under this surface. I don't even know what that surface looks like, but under that surface, over this region.
That's 1.
Listen, again, in 14.1, when you open 26, they just want you to do this problem. They want you to crank out some problems. But we need to practice sketching these regions. I want to take a look at this region. It takes some effort to sketch this region. The region, listen, you understand something. I don't want you to sketch the 3D thing. I don't want you to sketch the 3D surface here. I just want to sketch the 2D region over which I'm integrating. Oh, and the 2D region over which I'm integrating is totally described in these bounds right here. And these first bounds are for the variable x, and x must live between 0 and y. I mean, you can write that down. X lives between 0 and y. And at the same time, y lives between 1 and 3. I mean, writing that down sort of helps. I would just I'd rather just go start drawing this. X equals 0 is this. X equals y is this. This time it's different though. My x lives between 0 and y. My x, which moves sideways, left to right. My x lives, my lower bound of x is a 0, and my higher bound of x is y. So my x lives in here. And while x is doing that, see, I could shade this whole dang thing, but wait a minute. I'm also restricted by this. Y lives between
1 and 3.
1 and 3. So do we have a good sketch of this region? Maybe. There's 1. There's 3 for y. And so we must be between 1 and 3. Well, yeah, it must be this. It's really not this. Or this. You guys okay?
Yep.
When you read these bounds, you're sketching the bounds. That's the region over which I'm integrating. We spend a lot of time sketching that. We don't really care about there's a 3D thing up above this, and I don't need to sketch it necessarily. Not yet. Here's one. Check this out. I'm going to do 46. 46. In 14.1. This 46 is kind of funny. You got this double integral. They got specific bounds, but then they got this function in here, and it's not specific. So I'm doing this. So I can't really do any integration here. I got this function that's just this generic function. I'm integrating dx dy though. They did have this specific order, dx dy, and the bounds are square root of y to 2, 0 to 4. Square root of y to 2, 0 to 4. Now, first of all, I'd like you to just observe how these things are set up. They're very typical like this. Look, the first variable of integration is x, and the bounds are in terms of y's, or numbers, or y's. And then the next variable is y, but he's also the last variable, therefore his bounds are just numbers. They don't have variables over here, just numbers. That's typical, that's how it's set up. Now, in this problem, what they want me to do is sketch the region of integration and switch the order of integration. So what they want me to do is, they're going to want me to switch this. Again, I can't really integrate it because I don't have a function, but they want me to switch the order of integration. That's a typical problem that we like to do. And what that means is, instead of dx dy, I want to switch the order and I want to do dy dx. But switching, listen to this. Switching the order of integration. I mean, yes, I got to change these bounds, but it's way more involved than just, oh, let's just switch these bounds. It's totally way more involved than that. Here's the procedure. The procedure is draw a picture of the bounds that exist, and then you have to rethink the picture with y going first and x going last. But you have to draw this picture, so that's why I spent a little time already today trying to draw this region. So here we go, I want to draw this region. what's going on in this region. X equals the square root of y. That's one of my bounds. In fact, that's my left bound. Why did I call it a left bound instead of a?
On the bottom.
Well, sure. Would I call him a left bound?
We call them a bottom.
Bottom bound.
Yeah. Well, because he's x, because he's a bound for x moves left to right. So the lower bound of x is on the left. The upper bound for x is on the right. The lower bound for y is
On the bottom.
below the bottom, and the upper bound for y is the top. Right. But I want to sketch x equals the square root of y, which I think is like y equals x squared. I think it's this.
Just that half of the parabola.
It's just that half of the parabola. X equals the square root of y. Wait a minute now. That's my left bound?
Yeah.
All right, where's my right bound?
So,
X equals 2? X equals 2. Well, how do I draw x equals 2?
go 2 to the right.
X equals 2.
Yeah.
These guys must hit each other here. In fact, where do they hit? When x is 2, hang on. When x is 2, I think y is 4.
Yep.
Y is 4 here. Wow, this is cool, you guys. Look, x equals the square root of y is the left bound. X equals 2 is the right bound. So the x must live in between here. Is that what it's doing? That's the left, that's the right for x. For x, that's the left and the right. And while it's doing that, what's y doing?
0 from 0 to 4.
0 to 4, which is perfect. Y equals 0 is this lower bound, and y equals 4 is right there where they intersect, actually. So this is it. This is a beautiful picture of this region. Okay, so now I just want to rethink this region, and I have to let y go first. So now y goes first. So y is a stick that goes from the bottom, lower y, up to the upper y. See what you do, you draw it arbitrarily in there, you guys. You kind of draw it. It could be here, it could be here, it could be over here. And anyway, no matter where you drew it, what's his bottom? Y equals 0 is his bottom. And what's his top? Oh, that function. Y equals, oh, well, right now the function is called x equals the square root of y. But I think I'd like to solve it for y in terms of x. So if x is the square root of y, y is x squared. Right? So y goes from the lower bound of y is y equals 0, and the upper bound of y is y equals x squared. See, it has nothing to do with that. Well, it does have something to do with it. It's that function, x equals the square root of y, solved for y in terms of x. You got to solve it for, it's the same boundary I had, but it's renamed. I got to rename that boundary as a function of x. Hey, while it's doing that, I think we got y taken care of. What should x do? X is last. X is
should go
0 to 2.
just 0 to 2. See, when whoever's last is easy. It's just 0 to 2. You've already got the arbitrariness of this stick here, and now you just want to move that stick from 0 to 2. But notice, look at those bounds. I mean, they came from this region, and this region came from those bounds. But you can't, in your head, you can't go from those bounds to those bounds. You see what I'm saying? Mm-hmm. You got to go to the picture. You take those bounds, draw a picture, rethink the picture to come up with your new bounds. And what we just did was switch the order of integration. We can't do this problem because there's nothing to do. But we accomplished what they wanted. Switch the order of integration. And that's a good skill because you might make it might be something that's hard to integrate. But when you switch the order of integration, now you make it easier to integrate, perhaps. right, let's do one. I'm gonna do one more and then I'll quit. I'm gonna do 68. I'm in 14.1. This just drives this last point home and then we'll quit. 68 gives me this problem. It's a double integral. It's e to the negative y squared dy dx. And it's got some bounds. X to 2, 0 to 2. X to 2, 0 to 2. One more time. You know, the bounds for y are sort of in terms of x's. The bounds for x are just numbers, the last numbers. What they say in this problem, if I read the directions, they say, note that you cannot do this damn integral. That's what they say. They probably don't cuss like I do. Maybe a little more, a little better. You cannot do this integral. You can't, because I don't know how long it takes you to think about it. Trying to integrate this with respect to y, the variable is y. I can't really integrate this with respect to y. That's kind of like that one I was trying to do earlier today that I erased and redid. I couldn't do it. And so you cannot do this with respect to y.
Switch the bounds.
So what they suggest is if you switch the bounds, and by the way, if you did switch the bounds, which is going to take a little work, but could you integrate this with respect to x? How do you integrate this with respect to x?
Add an x.
Oh, multiply by x?
I mean multiply, sorry.
Yeah, that's okay. But I know what you meant. Multiply by x, right? So now you can do it. Because he's a big constant. And you integrate with respect to x, and you just get x e to the y squared. Hold on a minute, though. We got to switch the bounds for this to officially take place. And in order to switch the bounds, I need to draw this region and then rethink the region like we just kind of did. What is this region? These are bounds for y. What I have here is y equals x. Y equals x. And what I have here is y equals 2. Y equals 2. Now wait a minute, who's the lower and who's the upper? See, you can shade the wrong thing fairly easily here. Y equals x is the lower bound, and y equals 2 is the upper bound. Oh, I must be in here, right, you guys? Mm-hmm. And while I'm in here, that's what y is doing. X is going to go from, what's x going to do? X is going to go from 0 to 2. Oh, which is perfect, because that's what that point is. X goes from 0 to 2, and y goes from x to 2. Yeah, here's a picture of this region. All right, now,
X can go from 0 to 1.
let's rethink this region. We got to let x go first. I got to let x go first. X goes from left to right. So x would go from an x value on the left called x equals 0 to an x value on the right called x equals y. Right, 0 to y, exactly. While y does what?
It goes from 0 to 2.
0 to 2. Cool. Okay, so now we can do it. We drew the picture, we rethought the region. It wasn't too hard on this one. We set up new bounds with this order of integration switched. We switched the order of integration. And now we can integrate. I already said you would just multiply by an x. Let's work on this. My bounds are 0 to y. I'm plugging those in for
your y.
For my x,
yeah,
actually.
sorry.
That's okay. I plug them in for my x. Plug that y in. Oh, so then I get y e to the negative y squared minus 1. If I plug in a 0 for that x, that's just 0. So that's nothing. That's it, you guys. Now I want to integrate that with respect to
dy.
To y from 0 to 2. Now can you integrate that?
Yeah.
Yes, thanks to u substitution, you can do it now. You couldn't a few minutes ago, but now you can. You can let u equal negative y squared. What's du? Negative 2y dy I'm happy to have that extra y dy. That's going to kill this y dy. This problem turns into e to the u. Hold on.
Spit out negative half.
Spit out a negative a half du. That's how you do this. Right. Now how do you integrate e to the u? E to the u. It's a negative 1/2 e to the negative y squared. I'll plug in my bounds, 0 to 2, and we'll be done. Plugging in a 2 gives me negative 1/2 e to the negative 4 minus a negative 1/2 times 1. Woohoo! That's it. That's pretty cool, man. That's a 1/2. I'm just going to change that. That's a 1/2 minus 1 over 2 e to the 4th. I just swap the order and change that around a little bit. You could get a common denominator. E to the 4th minus 1 all over 2e to the 4th. Anyway, enough's enough. Enough is enough. What is that? That's a number. What is that number?
0.491.
Yeah, I thought you were going to say it was my number when I played quarterback. What is that number though? Okay, thank you. It's a number. What is
I
it?
got 0.491.
Okay.
Approximately.
What is it?
What is it?
Yeah, what is it?
Isn't it the bottom of the...
It's the volume of something that I can't see here. Right. What I do see is the base. This is the region over which I'm integrating. Technically, there's a z equals this thing, lives up above this thing. It must be pretty damn close to it. It's got this, it doesn't have too much volume, apparently. It's 0.491. Okay, that's good. All right, let's quit today. Thanks for listening. So we're sort of in 14.1, 14.2. I'm going to hand you a bunch of stuff back.